Okay, welcome to the online causal inference seminar. Today we're excited to have Vanessa Didelez talk about causal reasoning in survival and time to event analysis. In Q&A, we have one of her collaborators, Mats Stensrud, and also Vanessa will stop from time to time to take questions. So please, if you have any questions about the talk, submit them. After that, we have a discussion by Goetghebeur. And after that, if we have some more time left, we're gonna take some more questions from the audience. Questions today will be handled by Guillaume. So I'm now switching over to him.
Thank you, Dominique. So as usual, questions will be handled through the Q&A. We're lucky to have Mats manning the Q&A today. So please ask questions. We will select some questions to ask to Vanessa live. So the question selected, if I select your question, I will ask you to unmute, to raise your hand, and then I will unmute you. So please don't raise your hand unless I've asked you to do so. All right, thank you very much. And Vanessa, whenever you're ready.
Okay, can you see my slides? Always the first question.
Yes.
Great. So thank you so much for inviting me to this great seminar series, which I have enjoyed very much. The Tuesday evenings have become the highlight of my week. And it's also nice to see so much diversity in the topics in this field, and also to see a bit of controversy. So for some reason, I can't move my slide. There you go. One thing that is not so controversial is that a cause precedes the effect. I think most people will agree on this. But nevertheless, in the typical causal models, time or the dynamics do not really play much of a role. So this is what I want to talk about today. And in particular, when we include time in our models, then we have to acknowledge that other things can also happen in between the cause and the possible effect. And this is something that we might want to take into account, or at least be aware of it and then choose to ignore. So something to think about. Let me give you some examples. Some of these things that might happen in between can affect the treatment. So they modify the treatment. For example, non-adherence to treatment. Let's say you are carrying out a screening program for cancer. People start later than they should, or they stop before they should. They are irregular, or in other contexts, you might have treatment switching. So this changes the definition of the treatment, and it happens over time. Other events change or affect somehow the outcome. So they might make the outcome invisible or undefined or ill-defined. One of these is when you have competing events. So let's say the event of interest is death from cancer, and a competing event would be death to other causes due to other reasons. Other things that can happen in between are things like unintended side effects. For example, immunotherapies can trigger anti-drug antibodies and thereby reduce the effect of the therapy itself. These sort of things have also recently been addressed by what is known as the ICH E9 addendum, and they are called intercurrent events. So if you come from the pharmaceutical side of things, you may be familiar with this term. Note that all of these are post-randomization. So even when we have a randomized treatment, these are things that will affect the interpretation, the methods, the estimands that we choose. And of course, in survival analysis or time to event analysis, the whole reason why this is its own field, we have censoring. By the end of study, at the latest, observations are censored. There's also dropout, of course, but people also often consider deviation from study protocol or death due to other reasons, so competing events, as censoring. And here we have to remember that in the end, what we want is inference for an uncensored system. So we need to take this into account. So in face of all of these various aspects that can happen over time, affecting treatment, outcome, and things in between, it's important to formulate sensible and useful research questions. And in our field, of course, we formalize them as clear and explicit causal estimands. So I will start with some very basic things, estimands, identifiability. I will introduce a tool that I like to use, which is folded graphs. And I will say a little bit more about censoring. So first of all, a simple setting. Let's say we are interested in a time to event like death. And we have the simplest case, a binary baseline point exposure for now. What is the causal estimand? For various reasons, I think that it's very useful to look at the survival curves as a whole. So in a way, we are looking at the whole distribution here under the two interventions. So let's say we have binary treatment, we intervene to set it equal to A or A star, and these are the definitions of the survival curves or the survival probabilities. In view of the intercurrent events, what this describes is a total causal effect, because regardless of what happens in between, we are ignoring that, and we're just looking at these probabilities. It's also common to look instead at the other way around, at the cumulative incidences. So here in the causal context, at the interventional cumulative incidence functions. Again, remember that the estimand here is in terms of the uncensored outcome. So what about identification in this simple setting? Let's say we have a randomized trial. Then there are randomization helps with confounding, of course, but there are still 2 points to be aware. If the time to event is well defined, regardless of the possible intercurrent events, then you can stick with this estimand. And also if censoring is independent, which is not something that's guaranteed by randomization, not even if the only censoring is administrative censoring. So then we would simply estimate the survival curves or the cumulative incidences. There are many methods for this. Kaplan-Meier, the most popular. We estimate them in the treatment arms, and there you go. If you have non-adherence, then this will represent an intention to treat effect. Now, what changes when we have observational data? Let's say we are using health claims data to evaluate the effect of mammography screening, for example. Of course, in addition, we have to adjust for baseline confounding because we can't exclude this by randomization. Let's assume we have enough covariates measured to believe in this. But this is not the only thing, because one of the big problems is that, especially for health claims data, for example, it's not always clear what the baseline actually is. You have to define this very clearly. So you have to have a clear definition of time zero. This means is you need to align when people become eligible for the trial, when is treatment assigned in your database, when do you consider this as the assignment, and when does follow-up start. Very helpful in this context is the target trial principle. And I will come back to this. That's why I mentioned this here. This will force you to, if you follow the target trial principle, you will set all these things so that you have a well-defined time zero. Notice that I've so far avoided hazards. Estimands are in terms of survival probabilities or cumulative incidences. This is in contrast to much in the survival literature, where it's popular to contrast hazards, hazard ratios, risk ratios, etc. However, the causal interpretation has been discussed recently, or actually in the last 10 years, to be a bit problematic due to the conditioning on survival. So hazard is a rate conditional for those who are still alive at the time. But hazard models are, of course, still useful as a tool, and we will use them still. I want to also mention that we can put the very simple setting that I've given you so far into a bigger context of, let's say, marked point processes, where we have different types of events. These come in terms of times where events occur and types of events. You can count these with different counting processes. They have some nice mathematical properties. If we have time, I will come back to this at the end of the talk. But in terms of processes, I'd like to briefly give you an idea of these folded graphs. So this here would be the folded graph when the unfolded graph is across the different time points. So if you have discrete time, you can use the nodes at different time points for the different variables that you're observing over time and draw a DAG or whatever graph you like that seems suitable. The folded graph basically folds this together, and the nodes are the processes. And you would omit, for example, an edge from Z to Y here if at any time Y doesn't depend on the path of Z, given its own path and that of the other processes. So there is a relation between the absence of edges and paths in the unfolded graph and the folded graph. Based on this, we can define suitable separation in the folded graphs also, but this will be asymmetric because we are separating the present of a process from the past of another process. So a bit of discussion about this. Unfolded graphs, of course, they can contain more details about the structure, especially relevant when it's not stationary, but the folded graphs are more compact. With discrete time, you have to be a bit careful because you're marginalizing over the intervals between the time points. So sometimes it might be necessary or appropriate to add undirected, bidirected dotted edges or something like that. In continuous time, we don't really have an unfolded version because we don't have discrete time points, but we can think in terms of nodes representing the past and nodes representing the present. Sometimes it may also be more appropriate to show self-loops in order to make clear that a process depends on its own past. I'm not usually doing this. I just always assume that a process depends on its own past. If you want to read more about this, I don't have the time to go into any details, so there's lots of references at the end of the slides and you can download these. So let's use these folded graphs to think a bit more about independent censoring, which is an assumption that's often needed. So let's say we have a treatment process A and an outcome process Y. Then in this case, when the present of the censoring process the past of the censoring process doesn't affect the present of the other processes, then we have independent censoring in the sense that the events do not become more or less likely after censoring than they were before. When would this be violated? So you would think, well, if there was some edge like this from the censoring process to the outcome process, say. However, as we often think of censoring as something that just makes things invisible, so the end of study or dropout or someone somehow disappears, this is often not really the causal structure. It's more that we have to think of something like confounding an unobserved common cause of the censoring process and the outcome process here. And then we can speak of conditional independent censoring, if you like. If we have data on you, then we can adjust for this. I will not spend much time talking much about censoring in the following. I will perhaps come back to this at the very end. So I want to now turn to the topic of separable effects, which we can use to deal with some aspects of what I mentioned earlier, the intercurrent events, for example. So let's first think of it in terms of possibly mediation or an intermediate process. We have a counting process that counts the event of interest. So let's say this is death. And we have an intermediate process, something like onset of a side effect, you're measuring the kidney function, or a competing event. So this doesn't have to be an event process itself for the moment. So whenever things happen in between the cause and the effect, people like to turn to causal mediation analysis. And the current mainstream causal mediation analysis is based on what's known as the pure or natural direct and indirect effects, which are defined in terms of nested counterfactuals. It turns out that for this sort of setting here, where we have a survival process and maybe an intermediate process here, this is not well defined and or not identified. Let me explain this a little bit. Just consider a simple case of two discrete time points, where here an edge from the counting process N to the mediating process M represents that for this to be well defined or to exist, of course, the patient has to be alive beforehand. Now, the direct and indirect effect notions here, they correspond to paths that are either avoiding all the M's or going at least through one of the M's in this case. So this would be the two direct paths. And this would be, for example, two indirect paths, the green one and the blue one. And as you can see, the node N1, so prior survival, already appears as well in the direct as well as in the indirect path, which is in some sense the reason for the lack of identifiability. More time points or continuous time doesn't make this easier. So we always have this problem, at least whenever we have a process as a mediator here. So instead of doing this, we can think about what is the target trial in our case here, or what could be a sensible target trial. And maybe this will guide us to an interesting estimand. For the natural or the pure effects, direct and indirect effects, it has been discussed that crossover trials where you first assign one treatment, then you measure the mediator, then you wash out, and then you set the mediator to the value that you observed before, but the treatment to something else, etc. This is impossible when you have a survival outcome because you can't repeat that. So that's out. But another design, maybe as useful as a target trial, is something that is actually being carried out, namely placebo-controlled blind studies, which are studies, they are designs that actually isolate the direct effect of the active ingredient. And this leads us to what we call separable effects. So what is a separable effect? We assume, for the separable effect, we assume that treatment actually has at least two components. And these components are, maybe you can understand them as the mechanisms that stand for activating the mediating path and the direct path, if you like. But observationally, our data is characterized by the fact that these are always equal. Okay, so I've said this, this is the interpretation of these components. So in the placebo trial, you can think of AM as whether the person thinks they are being treated, and as AY, whether they actually get the active ingredient. And now what we are interested in is a hypothetical intervention where we set these components to different values. So even though observationally they are all equal, we are interested in setting them to different values. In the placebo trial, they are actually not equal. They are being set to different values because you give people a placebo, which is a pill without an active ingredient. So this means that in terms of these separable effects, our target of inference becomes maybe the survival curve, where we set one component to one value A and the other component to another value A star. So depending on which one you vary, you have either the direct effect or the indirect effect of these separable components. In terms of path-specific effects, this corresponds to actually partitioning the paths that go out of the treatment into those that start with an edge into the mediator process in this case, and the other paths that start with an edge into the survival process. Now, it may seem a bit strange, these separable components or components of treatment, separable effects, but once you put the idea in your head, you actually find examples everywhere. The first one I already mentioned, the blinded randomized controlled trials. That is not even a hypothetical design, it's an actual design. Another example, I'm told that there's research on removing from marijuana the hallucinogenic effect so as to use it as for its medical reasons. Or in a completely different example, weight loss programs, they often combine a social aspect, which definitely affects the attitude and the actual change in diet. And there are many more examples like this. They may not always correspond to actually the mediator that you've measured, but there are definitely a lot of good examples for separable treatments, separable exposures. And I think this is a possible point where we could break for questions if there are any.
Thanks, Vanessa. So there are no questions at the moment, so maybe you can continue, and that will give us more time at the end.
Okay, so I will now talk a bit about identification. If anyone has a question by the end of that, I can happily break again then.
Sounds great. Thank you.
Okay, so about the identification of separable effects, we start with this property. What this is saying is that imagine you do one trial where you randomize the original treatment, which is just one thing here. This will be this distribution, this interventional distribution. And then you do another trial, and that is now the hypothetical trial where you use the two separate components, but you set them to the same value, A and A here. Then this should be such that these interventions, which are different interventions, here you intervene on one thing, here you intervene on two different separated things. You should believe that they are the same thing. Otherwise, it's very difficult to make any headway when observationally we only observe the equal values between all of these. But remember that what we want is then to separate these to set them to different values. And this is then possible by the next assumptions. These assumptions are basically formalizing that the mediator is in some sense not directly dependent on the one component of the treatment, and the survival process is not dependent on the other component of the treatment. That's always given the past, given still alive, and given the relevant component of the treatment. And of course, in practice, this will be conditional on baseline covariates when you have observational data, and also the notation would be different, or the concepts would be slightly different when you have continuous time. Now, what does this give us under these assumptions? We then have that our interventional distribution under the separable effects is identified from the distribution where you just have one treatment. And how does this work? Well, we always fall back onto the mediational G formula in these things. So this is the survival mediational G formula, if you like, where we have terms that relate to the survival process, and they are under the single treatment A set to little a. And we have terms relating to the mediator process, which are under the single treatment but set to A star. And this, the assumptions allow us to separate these out like this. Okay, so maybe this is another point where if there are any questions, I can take some questions now. Did anyone come up with any time?
So there is there are kind of like two questions, and one of which is being answered by Matt, but maybe we can ask it. So one question is about whether assumptions 1 and 2 are cross-world assumptions, and the other one is about the difference between the separable effects and the mediator. So you can maybe say a little bit about the first one.
Okay, so no, they are not cross-world assumptions. These are because this is assuming that in a single word we can separate the components of the treatment and set them to different things. And like I was saying with the placebo-controlled trial, this is an actual trial where you do that, where you do pretend for some people you get a pill, but you don't have the active ingredient. So you are separating it into two different components and you are setting it in one trial for one person. It's not a crossword. So these assumptions would be verifiable in a hypothetical trial where you actually separate the components and set them to different things. So
okay, that makes sense.
Yeah, it's quite an important aspect, I think, that we want to avoid crossword assumptions, but this is mostly a way of thinking in a different way about this, whether you can, in one word, what is normally maybe across words, maybe you can put it into one word by separating out different components of the treatment. Okay?
Got it. Yep. Thank you very much.
I will carry on then. So when are these assumptions violated? Of course, that is related also a bit to the question. One violation would be when you really can't separate out the components in the sense that, let's say here, this component will still affect the mediator. This may be just that it's just not biologically plausible or possible, or from the biological mechanisms or whatever you're looking at, impossible to separate this out. If treatment consists of one thing, one ingredient, and it just does various things, maybe you can't separate them. So this may then not be interesting as an estimand in the first place because you can't separate properly. But in any case, it wouldn't be identified from observational data where all of these three variables are always equal. But the same thing actually occurs also if you have too little information or too few measurements, let's say, of the mediator process. So here you have a path which, if you don't measure this, it's an edge really from AM to N, and therefore for the same reason you would not have identification in this case. But this could be remedied by measuring the mediating process sufficiently frequently. Another situation where the assumptions A1 and A2 are violated is when you have a mediator outcome confounding. This could also be a process. This again could be remedied if you can measure U. We have worked out a bit more details for the particular case where we choose the additive hazard model, combine the additive hazard model with a linear mediator model. Now, these are quite restrictive model classes, especially the mediator model, the linear mediator model. But what I like about this result is that the math turns out quite neat, and you recreate what is known from path analysis. Let me just point out here. So in the hazard model for the survival process, you have the coefficient of the treatment and you have coefficients for the mediator process. And in the mediator model, you have the coefficient for the treatment. And it turns out that under these assumptions, also notice we are conditioning on people always being alive. We don't want to assume that the mediator exists when people are dead. So under these assumptions, we can actually derive quite nice formulas which follow the intuition. So the separable direct effect in terms of relative survival depends on the one path coefficient, the alpha, and the separable indirect effect in terms of relative survival depends on the product of the other two coefficients. And here's an example of an application where this is the quite famous sprint data. Treatment is an antihypertensive treatment. Outcome in this case is time to kidney failure. And I'm ignoring competing events here. And the mediation is the diastolic blood pressure. So the question here, first of all, is this separable? So we would need to separate components for the biological mechanisms that affect the diastolic blood pressure versus the kidney function. And this is a bit weird because, of course, diastolic blood pressure, it should be blood pressure altogether. So this is a little bit dodgy in terms of the separability. Right? The idea is to have blood pressure here, all of it, and not just diastolic, and the kidney function here. And in terms of results, these are in terms of the relative survivals. We can see that the total effect is definitely negative. So the treatment does affect the kidney function, which was suspected. And there's more of a direct effect and less of an indirect effect through the diastolic blood pressure. So let me come to the topic of competing events, which in a way can be regarded as a special case of what I talked about so far. So in competing events, we may have two events. One is the event of interest, let's say death from cancer, particular type. And the other event, the competing event, will be death due to other reasons. So only one of them can occur, and then the other one is undefined. We have our two counting processes for these events. So what is a sensible target of inference now? Remember that I was looking at survival curves or cumulative incidence before. So here we can now look at the event-specific cumulative incidences, which is the survival time or the probability that a particular event occurs before T under treatment setting. So if we, in a way, if we contrast all of these event-specific cumulative incidences for the relevant treatment values, that contains all information. It's basically saying we have a multivariate outcome, and we are looking at the effect of A on this multivariate outcome of the treatment A on this outcome. So if A is randomized, you have identification, or if it's an observational study, you need to assume no confounding between A and this multivariate outcome. Let me show you an example. Here, this is from a data set where the event of interest is death from prostate cancer, and death from other causes is a competing event. This was a randomized trial. The dotted lines are the competing event, and the solid lines is the incidence for the event of interest. Black is the treatment, and red is the placebo. So we see that the incidence goes down for the event of interest, but it goes up for the competing event. So treatment is helpful for prostate cancer, but harmful for death from other causes. So this is, in a way, the complete picture, but it's two-dimensional. So people often just want to know, well, what about the event of interest? So how do we interpret the cumulative incidence of the event of interest alone as a target of inference? This is, again, our total effect, but now also total as over across the mediating process of the competing event here. Another popular approach is that the competing event is treated as censoring. But this, as I said earlier, implicitly, or since a nice paper by Jessica, explicitly we know this corresponds to eliminating the competing event. So it's like an intervention to eliminate the competing event. So in this case, that would be death due to other reasons, which may appear a bit unrealistic. But this is corresponds then to the controlled direct effect. So in a way, both are a little unsatisfactory, the total effect, because we don't really know whether the incidence goes down because the other incidence here goes up. And the controlled effect is a bit weird because we don't want to assume that we can eliminate death due to other causes. So I would say separable effects are an interesting alternative to think about. To think about components. Can we separate the treatment into these different components corresponding to our two processes. And then our target of inference becomes the cumulative event-specific cumulative incidence under our separable treatment intervention here. Let me show you this with the same example. Well, again, from before, remember red is the placebo group and black is the treatment group. So the difference between black and red is the total effect. And now we have the green line, which is the incidence under this hypothetical intervention where we set the two components to different things, treatment for survival and placebo for the mediator. And we then see that there is a very small indirect effect because these lines are not very far apart, and a large separable direct effect. Again, we have to ask, is the separability a sensible assumption here? And in this particular example, the treatment was had something to do with estrogens, and so they have a testosterone suppressant effect, which is the one that's considered relevant for prostate cancer in this case. And they also have other effects, which are the ones that are relevant for maybe cardiovascular disease, which would increase death from other causes. Okay, in this example, let me just add this. The assumptions, of course, have to be satisfied, and they are a little implausible because we are only using baseline covariates, or we only had baseline covariates available. So there are extensions, series of papers, Matt has been very active on this, to both time varying and post-treatment confounding, also to continuous time, and also when the mediator event itself is something that you might want to condition on. Okay, another break for questions.
Thanks, Vanessa. Yeah, so we have a question from Eric. Eric, I've allowed you to speak, so you can unmute yourself.
Okay, thank you. Vanessa, this is going back a few slides where you discuss the recanting district, and you suggested that if you measured you would again recover identification. But I don't know if you were implicitly assuming that U was not an effect of the treatment, in which case, even if you had observed U, it will not be identified. So I wonder if you could maybe just also focus on the identification issues due to confounding, time varying confounding in these settings.
You mean this one, right?
Yeah.
Yeah. So with the absence of edges from anything here to U, I'm assuming that it's not a post-treatment confounder. But of course, you can also have, that makes it then even more problematic. And then even by measuring U, we will have a problem. But actually the problem, so you are referring to the post-treatment confounding problem with natural effects, where even when we measure the post-treatment confounder, we don't have identification. So in this case, with the separable effects, we need to define what we mean with the treatment components then, because if treatment is affecting you, then maybe we need a third component, or we need to say which of these components does go into you. So there is more thought to be put into this. And there's a paper about this. I believe you are a co-author of that as well. So there's more thought to be put into this when you as a post-treatment confounder.
Okay, thank you.
Thank you. Yeah, so yeah, maybe you can continue and we can keep some questions for the end if there are more.
Okay, let me see, where was I? Okay, so I want to just end with giving you a bit of an impression. I think that we can put this into a bigger framework, even though we haven't worked out everything yet, shall I say, of marked point processes or processes in more general, where we also have time varying treatments and we use the folded graphs, etc. So let me give you an impression of this. This will not go into any mathematical details. I only have a few minutes left. I already introduced the marked point processes earlier. They have nice mathematical properties, in particular this decomposition into a predictable process and a martingale process. And this is where the notion of dependence or independence will come in. And just to fix ideas, we might have counting process for the event of interest. We might have a competing event or occurrence of a side effect. We have the censoring event. We have the treatment event, like start of treatment or frequency of treatment, etc. So I'm now talking not about a point treatment anymore, but about treatment itself being a process, an event, switching treatments, etc. The folded graphs now in this context have been introduced as local independence graphs because they represent this notion of local independence, whereby a process K is locally independent of process J given the rest, if the predictable part from this Dobmer decomposition can forget about the past of this process. So it's not relevant for the predictable part of the process. Then we have this local independence. It's an asymmetric notion of dependence, and therefore we also need a new type of separation. Won't talk about this, too complicated. Graphically, what it means, we omit an edge from J, which is the past of this process, to the K, which is the present of this process, in a graph on all these nodes. And now we can think of these as graphs a bit like causal graphs, but what is our intervention here? And we are proposing to look at an intervention which is a stochastic intervention. So instead of saying an event has to occur at a particular time, we modify its intensity. So it has to be more frequent, it becomes more frequent under the intervention, or less frequent under the intervention. That might represent starting treatment earlier or later, changing the frequency, etc. Now, a graph, the local independence graph, is then causally valid if the intensities of all the other processes represented in the nodes in the graph remain the same under this intervention. Note also that we can represent censoring and the elimination of censoring as an intervention on its intensity. As I say, I'm not going into details, but under these various notions of dependence and graphs, we can obtain a graphical characterization of the identification that tells us when the interventional distribution, eliminating censoring, and the changing the intensity of treatment are identified. And this is a bit one of the more complicated structures that is allowed. So you can have all of these unobserved processes, U1, U2, U3. This is a censoring process. This is a treatment process. These are observed covariates, and this would be our outcome process. And various other things would immediately destroy the validity here. And then one way of doing the inference is by reweighting. And in this case, we have weights, reweighting representing the reweighting regarding the censoring and reweighting regarding the treatment, where we then change from the original intensity to the new intensities in both cases here. This is just a final slide with an example. It's a bit of a complicated example because this comes from cervical cancer screening, and the HPV test is known not to have a causal effect on the incidence of lesions because it's just a test. However, the different suppliers do different frequencies of testing. So we are thinking of representing an intervention where we make the frequency equal, and then we should see no association. But here, the two tests, the gray shaded area is the confidence intervals, is one type of test, and the incidence of lesions with this test, and the other, the green one is the other one. After reweighting to make the frequency equal, this one comes down to the blue one, but there is still quite a big difference. So that tells us that one of the two tests is not very good at detecting the HPV positives. It gives too many false negatives. Okay, so in conclusion, let me just do this quickly, not much time. There are many challenges in survival and time to event analysis due to these things that can happen in between. I think it's important to think carefully about the research question and the estimand, and that's what the talk was really about. Separable effects over a new point of view. I think they are more explicit about interventions, at least in treatment components, and they do require weaker assumptions than alternatives. We already mentioned the cross-world assumption, which we don't have with the separable effects. And we can put this into a wider context of causal relations between events and time, including time-dependent treatments. Okay. Here, some people who I have worked with, and I owe a lot to these, especially also recently the Stratos group. We are preparing a guidance paper on causal reasoning with survival outcomes. Thank you very much for your attention.
Great, thanks for the nice talk, Vanessa. We're now switching over to the discussion. So we have Els Goetghebeur present some slides, and after that, we're gonna, first Vanessa can respond, and we're gonna take some more questions if time permits. So Els, whenever you're ready.
Yes. Thank you, everybody, and thank you very much, Vanessa, for a stimulating talk. I must admit, I find these questions very difficult, and also from a practical view, the thought experiments, how to link them to data, quite challenging, but that makes it all the more fun to do. So what can I add is mostly questions, and a reflection from what I understand is also quite relevant today. And I realized as I was thinking about this that I have worked with competing risks right from day one on the PhD thesis. And it gave me an opportunity to think back. Was it stupid what we did at the time or not? Or how much better could we do it today? And in doing that, you know, even just an understanding of the endpoints of a competing risk standard, disease-specific death versus other cause death, is already not all that simple. Things are interconnected in real life very often. And so even separating out clear cause-specific deaths from one another may already be a challenge sometimes. You could wonder, is it an assumption or a definition of the endpoint? Could we think perhaps of, and turn things upside down, is it that what can be altered by a specific treatment? Or how do we do that? And treatments, separate them out. You know, most of the time when I hit treatments, they seem to interact with lots of others, and even with grape juice. So how realistic is it to hope for treatments that might just attack one or another, cause specific death, and nothing in between? So, of course, in your real world, you had one treatment that made the two separations of the components encounter non-positivity in the data. You need new data and the new experiments, and then you will need consistency of the separable treatment assumptions in your data and how it pans out there. And again, I'm looking forward to going through the challenge of making that stick. So I have a few, as I said, remembrances of the old days, where perhaps very much without thinking, we were used to have quote unquote separable effects, but of a quite a different nature. We thought of a cancer treatment just acting on the cause-specific hazard of death from cancer and not on anything else. So this is from the past century, but that was how these studies, randomized studies of treatment, were analyzed, also with a cause-specific log rank test, often knowing that maybe we lack the cause, it wasn't recorded well, and then some methods were proposed to help recover a cause-specific analysis, which seemed so much more powerful than doing the all-cause effect analysis. Of course, things like that also became quite interesting in large-scale vaccine trials, where if you could work with it, and this is an old paper again, with that idea, you could save a lot of patients in a vaccine trial. And these days, obviously, lots of vaccine trials around. You might wonder, might this help us forward and indeed save matters to a degree? Not acknowledging, of course, that especially a thing like a vaccine for an infectious disease has to also encounter a non-interference as an assumption. And at the same time, it'd be a bit strange that a treatment or a vaccine only works on one type of outcome and not on another. But even so, if it does seem to pan out, because after all, the cause-specific hazards, they are, say, observable in the data. If you have non-informative censoring and you have your treatments randomized. So as a result, you can check on the data whether it's true or not, to a degree, that your treatment only affects the disease-specific hazard and not the other one. And if it is true, then you have a relatively simple model. And you also know that if the treatment has no effect, then it won't affect either cause-specific hazard. So why not call that quantity that is playing there, even if it is to a degree time varying, which we can also easily measure these days and estimate? Why not call it causal, even if it's not simplistically causal, but it does express, I think, in a decent way, the causal effect of the randomized treatment, even if you then use these guys to report cumulative incidences as one would. Now, having had the pleasure of recently analyzing data from hospitalized COVID patients, some 8,000 of them in Belgium, who were subjected to low-dose hydroxychloroquine treatment, and that's quite important because it makes a difference, we think. But what I just want to point out here from that recently published analysis is that the tricky thing is, and was here indeed, that you had baseline conditions of these patients in an observed setting. This was observational data. That were to a part expressing pre-existing conditions and to a part expressing the clinical features with which these COVID patients came. And in terms of the imbalance in these covariates, baseline covariates, the story was quite reversed for the two of them. So when it came to the presentation of the COVID symptoms, it was quite clear that those who received the hydroxychloroquine in the Belgian hospitals came with much more severe symptoms on the whole than the non-HCQ treatment group. When it came to pre-existing conditions, and not surprisingly, cardiovascular disease conditions, say, it was the opposite. So the hydroxychloroquine observed treatment arm had less of them, since there was some indication that it might be counterindicated and there's a side effect linked to that, whereas the non-HCQ had more of these patients. And so the question is, with that at hand, how do you think these separable effects and treatments could work here, and what is done there? Now, I want to just briefly go to one published study in the New England Journal of Medicine last May that many of you may have seen, where I did worry about a lot of the basics already of approaching this. And so what did they do? It was a single hospital in New York, adults with a positive test results for the virus obtained at any point during the hospitalization. Of course, you have immortal-time bias creeping in right there, but it wasn't very bad. And, in our own analysis, we could handle that reasonably well. So we weren't too worried about that. But so they were followed. So these patients entered during the first wave. They were followed through April 25. So it's not all that long. And then at that point, the endpoint was time to death or intubation. So anything very serious happening. And what the alternative was that these patients were discharged alive from hospital since they recovered from the worst of the first acute episodes, or they were censored as we would typically know it. They were still in hospital at the time that they closed the study, April 25. All right. So what did these authors do? They treated the discharge alive as censoring and used Kaplan-Meier curves first to show the time to death, all caused in hospital in that case, treating the live discharge not even as competing risk, but as censoring, and dealing with the imbalance that might exist in the treatment groups at baseline. So here's the censoring indication by inverse probability weighting. And their key result that they published was a cause-specific hazards analysis, but involving this non-informative censoring assumption. So a hazard ratio there, they had very close to 1, and a confidence interval including 1. And then they showed also the cumulative incidence, I would say, of death in hospital, censored by discharged alive. And here you see that for the 2 treatment groups, the 2 curves were quite close, and they clearly felt sort of protected by the fact that for the Kaplan-Meier curve shown here, they used inverse probability weighting to sort of account for baseline differences between the 2 treatment groups. But of course, the inverse probability weighting sort of reconstructs 2 groups that have a similar combination of baseline covariates by the inverse weighting. But it doesn't help account for the informative censoring that might show up if I think the situation was presumably not that different in New York as in other countries in the world, as in Belgium. And here you see the profile with which the patients entered our hospitals with COVID as the pandemic evolved. And so this is the first week. This is March, and it went up to, in our case, we went up to May with our data analysis, but things like fever, cough, and perhaps no symptoms were completely severely present at the beginning of the pandemic because there was a fear of overcrowding the hospitals. And so only patients with quite a bunch of these symptoms were allowed to enter, and no symptoms, you had no chance at the beginning, but over time that changed. And so what we see here is that even just the ordinary censoring in this case was not non-informative, because obviously when you enter determines how long you're followed up for, and the non-informative censoring assumption, which the Kaplan-Meier curves embody, really means that in analyzing the survival curves, one assumes that those who enter late and who are, in our case, much better off than the original ones, since the censoring is assumed non-informative, their future hazard and/or cause-specific hazards are assumed to be similar to those of the early entries who we do observe in that future period. And so the bias of this story, to me, is rather striking, and we've seen it in some examples where we could do both analysis, that it was really quite different. So at this point, of course, we haven't involved yet the idea of separable treatments, which I think would be nice if we could have them here, to think about a treatment that perhaps handles maybe the side effects that have to do with cardiovascular disease that might be aggravated by the HCQ, versus something that is supposed to be no longer anti-inflammatory, because they've known that HCQ doesn't do that, but no longer antiviral, but anti-inflammatory and other properties that the HCQ had. And so, yeah, in the competing risk story and how we handle censoring, and in this particular case, discharge from hospital alive, I think there's so many basic things which are still ignored and still hardly understood, that I really welcome the sort of things that have been presented here that are at this point a thought experiment of how the separable effects could enter and be seen, in theory seen, and then applied. But the fact that we're still having these highly prominent journals come up with such things, and this just expresses what I've just done, is really worrisome to me. And of course, outcome regression-based methods and G-estimation are much better in a setting like this, because they can incorporate also the covariates that drive and in the end inversely probability weight them. But since we, in our analysis of our own data, have used competing risks to analyze this kind of thing, and since this was just published when we submitted ours, everybody told, none of the reviewers could understand why on earth we might choose a competing risks measure. They just, and it was good medical journals, they just didn't understand the concept. So my question is, what can we do to help things along as far as that goes? And how can these separable effects help people think about what might and might not work here? And how informative censoring enters into the picture. And I think interactions are very, very hard to exclude. So in our case, with COVID treatment, quote unquote treatments, there's the impact of the comorbidities that play a baseline, but they're not just confounders. There's an interaction to be anticipated between the treatment and the comorbidities. There will be interactions between the treatments, and of course, with the background severity of disease. So a bit of my question in a discussion fashion here, seeing how much trouble we had to explain what we thought was clearly better than what had been done dealing with these issues in the recent New England Journal article, and the referees don't understand it. How dangerous are many thought experiments with intricate untestable assumptions in times of much fake news, where even the most obvious thing is so hard to convince people of, that the truth versus non-truth. So I think obviously the causal inference field has been bombarded with clearly biased analysis of data, and maybe also non-representative data. And I feel part of the COVID crisis is also that this has been aggravated and distributed around the world in a way that is really, really tricky. And so perhaps one thing that might help, which we, with the causal inference group of Stratus, the 7 topics group 7, have tried out, is to develop this simulation learner, which is not only simulating observed responses, but also, if you pardon the expression, the counterfactual responses to a bunch of possible treatments. So, this is one of the examples where we start with a randomized trial. It is going to a breastfeeding intervention, but then people, yes or not, take up the breastfeeding educational program offer. And then they, yes or not, start breastfeeding, and they may continue it for a longer time or not. And then at the end, there's a wait at 3 months for the babies, which we discussed there. But it's clear that also there, as we thought through carefully, because we simulated the counterfactual answers through all these potential potential exposures and outcomes as they would show themselves in sequence, that there were several things that we hadn't thought through well enough as we just analyzed the data. Then what we started thinking through these mechanisms and making them explicit, and actually generating through several stages the counterfactual responses of individuals to each sequence of these things, of these events, less complicated than yours, but we learned a lot, and we also learned how much we had ignored but before we went into more detail into these different levels. So I think it may be a way of making things concrete and showing where the biases and the wrong answers come up and how much they matter. And in fact, in some of our analysis, we have seen that the changing background over calendar time of patients entering can really have an enormous impact, not just on the Kaplan-Meier curve that is biased, but even more once that starts being inversely probability weighted. So And then, so it's one of the reasons why, in this case, we have started explaining things by stepping ourselves at one position at a time and working with the background into the future. And then, so as treating it as point exposures in turn and moving onward from that, with of course the past exposures then to account for. And things like whether or not, in this case, the randomized educational program is not having a direct effect on the result, but only goes to actually going to the program. That's already a question mark that in general is not so easy to push forward without much thought and knowledge of the real condition. So I think the thought experiments about separability are very intricate and are highly, highly challenging. And it would be wonderful to have a worked out example. A worked out example. And I just want to end with something my eye fell on today, as I'm an editor of Statistics in Medicine, which has its 40th anniversary coming up. And we were going back to, we will republish one of the old papers of Armitage on causality, not the traditional one, but an even earlier one. And I thought I should look what the aim of the journal actually states, because one of the co-editors had said something, and I think we are claiming more than that. And in fact, what the first sentence of the aims and scope of the journal says, that the journal aims to influence practice in medicine and its associated sciences, which is a huge aim, of course, for a Statistics in Medicine journal, through the publication of papers on statistics and on quantitative methods. So in fact, the aim and scope of the paper, the very first sentence, is about mediation and causality. And I thought, I've often felt that saying much about mediation is really highly, highly ambitious, especially from observational data, because much of these assumptions are so hard to justify. Of course, we cannot guarantee them to hold, yeah, so hard to justify. And even the standard assumption, the level 1 total effect, is often so ill understood, especially with survival data, where we have known for a long time that administrative censoring doesn't need to be non-informative. And it is not so in the long-term disease registries, which are starting to be a really great source of information on long-term survival, probably the best source that we have. But even there, since they are long-term registries, over these long terms, the entering patients change quite a bit, and it matters. And IPW Kaplan-Meier curves, which might be seen as robust, they're really quite biased if we're not careful. And it's not just in the long-term disease registries, but also in the short-term pandemic story, where things evolve quite fast, similar things play. So with this, a question on how might we do that in this setting? How certain are we that low-dose hydroxychloroquine doesn't work? That's another one that I think there's still a lot of debate on, and quite rightly so, which is different from the many standard hydroxychloroquine studies that have been done, and randomized studies which all used doses that are 5 times as high as what was used in Belgium. So there are lots of things there. But the fake news worry stays, and how to educate also the causal inference and the applied statistics community, who are doing things and publishing things in prestigious journals at a time that it really matters, and simple basic rules, especially with regard to competing risks and things that matter, like hospital discharge. But in my view, for the COVID story and the short-term horizon of time that one had, either you die in hospital, and if you were sent home, then we can safely say that within that number of weeks that we measure death in the hospital versus discharge alive, those patients discharge alive, they will survive these next few weeks. So discharge alive is not. Yeah.
Sorry to interrupt you. We're running out of time. Can you wrap up?
I'm done. Thank you. Yeah.
Okay. All right. Great. Yeah. As I said, we're running out of time. But Vanessa, do you quickly want to respond?
Okay, yeah, thanks, Els, for so many interesting aspects and of course very relevant in practice. I hope that the separable effects will not be seen just as a mathematical trick or something to do mediation analysis without thinking about it, but to really think harder about the problem and about the research question. And what we want in the face of competing events and other things, other mediating processes. So it's not going to solve all the problems. I don't believe that, but maybe some by making people think harder about where it matters in terms of interventions, in terms of changing something in practice.
All right, great. Thank you, everyone. So first, thank you so much, Vanessa, for interesting talk. Thank you, Mats, for helping out in Q&A, and thanks, Els, for a very interesting discussion. And next week we have Xinguan Zhao from Cambridge University, who will talk about selection bias in 2020. We're all very much looking forward to that talk. Thank you all for coming, and I hope you stay safe. Thank you.